All right, let's begin. Happy Friday, everybody. So today we're striding into chapter 18. I'll talk about that in a second. I'll be available after class today in the dining hall, probably until around lunchtime, 11:30. 3 to 4 in the dining hall. I'd forgotten when I scheduled when I said it was 3:30 to 4:30 that David Sloan Wilson is talking at 4. I would definitely recommend attending this. He's a very well-known evolutionary biologist, prolific and provocative writer, big thinker, provoker of strong responses. So it should be interesting for sure. And then, yeah, we should get through 18.1 and start 18.2, and I'll probably do a little more with 18.2 and then trudge into 18.3. Questions? All right. So let's start chapter 18. So in chapter 17, we learned about two types of sort of geometric objects, parameterized curves through space, and then vector fields, which we played around with last time. And now we're going to start doing things with those things. So how's that for a specific introduction? So let's say we have a vector field. And we'll call that F. And let's imagine it's a particularly simple vector field. It's just some sort of constant. The wind is blowing across the Great Plains or something. And then maybe you decide you want to go along some path R, and you kind of wonder, is this wind going to help me or is it going to hurt me? And you'd look at that and you'd say, okay, well, it's kind of at my back. It's going to be helpful. So that's a good thing. And then you might wonder, how much is it going to help me? And so I would want to know how much of F is in the R direction. Does that ring any bells? That's going to be a dot product, yep. So does F help me? Yes. How much? It's going to be something like that. It's going to be related to the dot product. And I'm sort of deliberately doing this in a kind of vague, not exactly a specific application setting. Those who have had physics recently might recognize this as an awful lot like work, f.dr, but there's usually a minus sign there. So anyway, we'll just worry about f.r right now. OK, so that's that. No, relatively straightforward. But it's college now, and so maybe you decide, I don't want to go in a straight line. You could decide, well, all right, I feel kind of good about this. I don't want to make a mess of this diagram. But you could decide, what if I go this way? Or maybe I want to go this way. Particularly at COA, we're really not about straight paths anywhere, right? And of course, the vector field itself, it might not be constant. It could be windier here or here, or a stronger current here or here. So what might we do then? How might we get a sense, if we have a more complicated vector field, a non-constant vector field, maybe I should probably, so maybe we have something like this. And maybe we want to go from here to here, but we want to do it that way.
Did you integrate the dot products?
Yeah, so we're going to need to add up a lot of little dot products. So what I need to do is, if I imagine, well, OK, let me say it this way. We want to add up some stuff to get a total helpingness of the field. And the problem is the thing we're adding up is changing while we're adding it, because the direction is changing, your direction is changing, the field's direction is changing, all the stuff is changing. So we just divide it up into tiny little pieces and pretend it's not changing over that. That's what integrals do. So total help, meaning total help of the field, we would do something like this. And the picture here is if you zoom in on a tiny little region of this journey through a vector field, the orange curve becomes essentially straight, and the vector field is going to be essentially constant. And the usual game applies if I said, well, but this is a lie. You're living a lie. You're pretending it's constant over this small region, but it's not really. And then you would say, OK, well, I'll just let delta r get smaller. And I'll say, yeah, but you're still lying. And so you'd say, OK, I'll let delta r get smaller still. And eventually, this sum would approach a limit, some definite value. And that's what we call the line integral. So that goes to this, f dot drc. So this would be the line integral of f along the curve c. So let me see if there's... So before we talk about how to calculate these things, should generate a little bit of intuition about what they are. So chapter 18.1 is called the idea of a line integral. So this is the idea of a line integral. And now let's do some exercises that will probe your ideas about line integrals. So we can do this, and then we'll spend a little while learning how to actually calculate these things. Here we go. So it looks to me like C2, the path along C2 is the only positive one, because that's where the wind is at your back. You're going in the same direction as a field that's helping you. C1 and C3, you're perpendicular to the field, so it's 0. And you could see that the dot product of perpendicular vectors is 0, so you're adding up a whole bunch of zeros. The other two are negative, and it's a little hard to tell, but it looks to me like C4 is going to be more negative than C5. OK, so you have the wind at your back, and then when you come back down, the wind is in your face, but the wind has gotten stronger. Because the arrows are larger as you go down. Yep. Yep. Maybe that's what you're asking about arrow magnitude earlier. And so it's a little hard, again, it's a little hard to tell, but it looks to me like C4 would still be more negative, because there you're heading right into the wind all the time, even though the wind is less strong at that position. Does that make sense? OK. Great. So let me mention just a little bit of vocabulary. This would be called the line integral of this vector field along the curve C. And if you have a closed curve, that's called the circulation around that curve. And the integral often gets this nifty 0 through it. For the rest of the course, the notation is just going to get slicker and slicker. So this means it's a closed curve. It loops back on itself. And it's worth noting that direction around C matters. So like if each of you and your friend decide to do a circular hike, and one of them goes in one direction and the other in the other direction, you would have different reports about when the wind was in your face and when it was at your back, because you're facing in different directions. So this is nothing deep. This is more of just like a little calculational headache. All right. So that's the idea of a line integral. do you feel about that idea? Shall we talk a little bit more about how to calculate these things, more than just like get numbers instead of just saying plus or minus? So what I want to do, I thought I would do this. I would do an example through in a little bit of detail, and then some practice ones for you guys to do. So technically, we're now in 18.2. All right. So let's evaluate a line integral. So this is 18.2. Oh, by the way, for this one, I meant to ask for this vector field. Do you think could this be a gradient field? Could we construct could there be a surface whose gradient is this? So let's think about number 2. So for number 2, you should have found that the circulation was positive. All of those, because C2 is a little, C1 and C4 are 0. C2 is a little bit more positive than C4 is negative, because the arrows are larger there. So imagine then, if this is a gradient field, then these arrows tell us how much if we're going up or down on the surface. So then if I started in the lower left, I go up a lot. I go 0, I go down some, I go 0. So I do a complete cycle. I'm back to where I started, but I have a different altitude now. So that's not a surface, because there would be 2 possible z values. So I claim that this is not a possible gradient field. And we just noted that the circulation was not 0. That may be a clue for something that we'll probably do on Tuesday. Because I'd like to know, hey, is this a gradient field or not? We maybe have a way of testing now. But, OK. But before we get there, let's talk about how to evaluate these.
What happens if you have like a spiral?
And that would definitely not be a gradient field. So like if you had like a whirl, like if you had a field like this would say if you could just walk in a circle and you would always be going up. And so, I mean, you could have, that would be like walking up along a helix, but that wouldn't be a function because every x, y value would have multiple z values. It would be like a spiral staircase. Yep. Yep. OK, let's see. So let's do an example. So we're going to have f is going to be xi plus yj. It's kind of boring, but it's good to start with a simple one. And c is going to be line segment from 0 to 2, 2. So if you were wondering, gee, the material in chapter 17, I'm not quite sure I feel comfortable with that yet. Will I get to practice that again? Your answers, your dreams have been wished, have been realized. So this will sort of cycle back, and you will get to do a little more sort of working with parameterizing lines and so on. OK, so this means we start here, and we go there. So this is 2, 2. This is 0, 2. All right. Let's see how to think about this. So let me write. Let's parameterize C, and then I'll talk about what we're going to do with that once we do it. So what's C? So C is, let's see. So I'm going to start. Let's see. So y is a constant. And how do I think about x? Like I start at 0, and I want to end at 2. What would be a way to do that? So you could think of it this way, x. And y of t is just 2. So I could write this so how does this sort of make sense? So another popular choice, you could have just as well have said both of these do the same thing. You need to start at 0 and end at 2. And you could let t go from 0 to 1, and then you'll start at 0 and end at 2. Or you could write it this way and let t go from 0 to 2, and you'll start at 0 and end at 2. Because it's math, you'll get the same answer either way. When I did this problem this morning, I did it this way. But I mean, there's no reason to do one over the other. So, all right. So let's think about, OK, what are we going to do with this? So let me go over here. And I'm going to write this as f dot delta r. And I'm going to multiply and divide this by delta t. Surely that's a legal thing to do. Delta t over delta t is just 1. And you might say, why are you doing that? And I had said, it will be convenient. So notice what happens now. Delta r over delta t, that's going to be basically, yeah, I mean, it's actually the derivative of r. Yep. So this is r primed. So then this becomes f dot r prime of t dt. And then this is a normal integral. So this is a new integral. This is a Calc3 integral because dr is a vector. If we parameterize the curve in this way, we end up with a Calc1 or a Calc2 integral. Because now this is just a scalar. So this is a little abstract, but I think once you see this example, it will make sense. And then you'll do a few more, and it'll make more sense. All right. So this tells me that I need to, or so this suggests that I need to take the derivative of this. So let's do that. R prime of t, the derivative of, well, what's the derivative of this going to be? Just, yeah, so 1i, because the derivative of t is with, oops, I forgot that, sorry. The derivative of t is 1. The derivative of 2 is 0, because 2 doesn't change. It's constant. So there it is. It's a boring derivative, but that's OK. All right, so now I'm just about ready to do this thing. So I'll explain this notation in a sec. So I'm adding up a bunch of dot products. And I'm adding them up. Like what field do I use? I use the field, the value of the field along the curve I'm walking on. So what this is saying is, for the f values we use here, they're the f values you get along the curve r of t. And the curve here is a straight line, which probably really bothers Heather. May bother other ones. Sorry. We'll do an actual curve later, but straight line curves are easier to start with. Trust me. All right. So what does this notation mean? So all right. So 0 to 1. I want to plug in for the vector field. The vector field is x I hat plus y j hat. For x, I'm going to use this. For y, I'm going to use that. I dot that into the velocity, which is just I hat. And then I do dt. So if I do this dot product, I'm just going to get t times 1, because j dotted into I is 0 because they're perpendicular. Oh, sorry. I was still doing it the way I did this morning. This should go from 0 to 2. Sorry about that. 2. So, sorry, I see people diligently writing still. So let's just recap what just happened here. The j component of the field ended up not mattering at all. And that makes sense because we're not going up or down. We're just going left or right. I don't care if the wind's blowing this way. All that matters is the wind blowing this way. So this dot product just picked off the I component of the field. And so you get something like this. You'll get a big dot product. And then the next step, you're back to Calc 2. So this is just no vectors anymore. This is just you're just integrating t over with respect to t from 0 to 2. And we get a number. So the answer to this integral is a number, the sort of net oomph or help you get or don't get from the field, or the net work that the field does on you or something. All right. So there are two. I think the challenging part for these are a couple steps is sort of figuring out how to parameterize the curve. So work slowly, give yourself a lot of space. Once you've got the curve parameterized, then you can kind of like start doing this stuff. And then it's like a crank you can turn. All right, algebra dot products, I can do that. The part that's going to be a little bit tricky is parameterizing the curve. So we'll spend the rest of the day practicing this. I think it's worth doing a handful of these. And for reasons that for no reason at all, I put these in an order which is different than what I realized would be best for you to do. So I'm going to propose doing problem 1, 3, 4, 5, and then 2. And I'll write that down. So let's see. While we're swimming in the algebra, are there questions any of the mechanics of this? I mean, it's dot product. It's parameterized curves. So it's a bunch of stuff going on at once. Let's look at this geometrically for a moment. This one, right? So here's the vector field. This one is saying if you go along this path, does the vector field help you or hurt you? And it does nothing. It's perpendicular to you. The next integral you did was along this path. Same story. It's always perpendicular to you. It doesn't help you or hurt you at all. And that's why for both of these, you end up integrating 0. You're integrating 0. And the sum of zeros gives you a lot of zeros. So we go from here to here and here to here, you get 0 help from the field. On the other hand, if you take a different path, then that's this story. And here you end up with a 4, no matter how you parameterize the curve, which makes sense because it's the same curve. We just chose to parameterize it, to sort of describe it differently. You end up getting some net help from the field, and that makes sense because it's not exactly at your back, but it's definitely helping you along this path. So let's see. Could this field be a gradient field? Could there be a surface sort of behind this? Yeah, that's right. So if you and your friend start here, and one of you takes a hike like this, the other takes a hike like this, and you end up here together, you would have different altitudes. That would be exciting, but it would, but it means it's not a surface. There's not a single z value for every x and y value. So again, this is showing another way of saying this is like the path matters. For the sake of doing a curve that's actually a curve, let's do problem 2. So we'll do this problem one more way. Be a little bit more algebra, but it's sunny out. You guys can handle it, and then we'll be done for the day. So let's give number 2 a try. And presumably it's safe to erase some of this stuff? I'll definitely need some room. OK, great. What do you want me to get rid of? Can I get rid of the stuff on the left? This is going to be an interesting video. All right. So here's a circle, radius 2. And since we just want the first quadrant, we go from 0 to pi over 2. So here's the parameterized curve. I need to find its velocity. I take its derivative. Then I'm plugging into the line integral, blah, dot, blah. And I could have put this in here, but I knew it was going to be a long thing to write, so I thought I'll wait a step to write that. So then this is plugging in for y, and then x, and then this is just plugging in there. And then I have a dot product to do. So I multiply the I parts and multiply the j parts, add them together. This is a scalar now, and it's just an integral in terms of t. And then sine squared plus cosine squared is 1. That's the one trig identity worth remembering. And so happily, this turns into 4. This integral goes from 0 to pi over 2. So this gives me 4 pi over 2, which is 2 pi, which is 6.28-ish. And that's a reasonable number, I claim, because we saw that if we went from here to here in the straight line, we had a total oomph for help of 4. This time we're going around this way, so it's a little bit of a longer journey, but the field is always at our back, so that would get a little bit more help this way. So I guess like if this was a fluid flow, you could just drift along here, and because you're just following the streamlines, following the velocity field. This diagonal path, the one we did for 5, you get a little bit less help from the stream, so you would have to do a little bit of work yourself. So these are line integrals, and we'll do a little bit more of them on Tuesday, and then we'll also start talking a little bit more about what they mean geometrically, and we're sort of already a hint with that because you've seen that they're related to whether or not something is a gradient field. So we will do more with that on Tuesday. So I'll be in the dining hall in a couple minutes and can be there for a little while.